video, we're going to take a look at why we might actually use convolutions. So I'm going to suppose that I have a family of second-order differential equations like this. I'm going to keep everything constant, second-order initial value problems like this. I'm going to keep everything constant except the f. Now, everything that we're about to do mathematically is fine, whether a, b, and c are positive or negative. I want a to not be 0 so that this is actually second order. B or c could be positive, negative, or 0. However, in terms of applications, it makes more sense to think of a, b, and c as being positive, because then this corresponds to a forced harmonic oscillator. So the left-hand side, that a, b, and c would be determined by the spring constant, the damping coefficient, and the mass that we've got attached to our spring. And of course, the most important part of these problems is that we will have Moose, the massless mouse, going for a ride atop this mass attached to this spring. Okay, so if I'm not changing this, it's the same mass on the same spring, and of course it's the same massless mouse. We would not replace Moose. Okay, so I'm keeping that, and in the same condition, so with the same damping coefficient. I'm also going to keep the initial condition the same. I'm going to make sure that I always start at position 0 with velocity 0. What we're going to do is we're going to vary the forcing function. Now, if we vary the forcing function, we might be doing that actually because Moose requested that. He wants to know what forcing function is going to make the ride that he gets to go for on this harmonic oscillator the most fun. So we're going to do this experiment to try it out. Okay. So we're going to be solving a bunch of differential equations where the left-hand side is always going to be the same, but the right-hand side, the forcing function is going to vary. Okay, now what does that have to do with convolutions and Laplace transforms? Well, what I'm going to do is I'm going to look at a very particular element of this family. I'm going to take a look at what I get if I use as my forcing function the Dirac delta function at 0. So that's an impulse force at time 0. Okay. And I'm going to let z of t be a solution to this initial value problem. So again, I'm keeping these initial conditions. I'm just making the Dirac delta force function be my forcing function. Okay. So what I'm going to do is I'm going to find the Laplace transform for z. So if I'm calling it z, I might as well call it z throughout. Okay. So instead of calling it y, I'm going to just call it z. That's my solution for this particular forcing function. Okay. I'm calling it z, by the way. The book calls it, I think it's zeta. It's a Greek letter that I'm really horrible at writing. So I've just decided to give up. I'm going to call it z of t. When you're reading through the book and you see the squiggly thing, that's the Greek letter that they're using instead of z. If you're better at drawing Greek letters, you're welcome to use that symbol. If you, like me, struggle with your Greek letters, you are welcome to just call it z. Okay. All right, so I'm going to take the Laplace transform of both sides. And the Laplace transform of the Dirac delta function is just e to the 0 times t. Okay. So whatever that number is, I think it's a negative. Where's my formula sheet? Here it is. Okay, this is formula, yes, it's a negative. Doesn't make a difference when it's 0. That's formula 10, that we get the Dirac delta function at a is e to the negative a times t. But of course, that's just 1. That's what's very special about the Dirac delta function at 0. Now, I want to work out this left-hand side. So I'm going to do a little bit of side work for the Laplace transform of z double prime. Okay. So I'm going to just remind us that that's the Laplace transform of the derivative of z prime. So by rule 11, that's going to be s times the Laplace transform of z prime minus z prime at 0. But, of course, we're sticking with this initial condition. I just happen to be calling my solution z instead of y, so this is just 0. Okay. So that's going to be s times the Laplace transform of z prime minus 0. Okay. But that's s times, using formula 11 again, I'm going to get s times the Laplace transform of z minus z of 0. But that's just 0. Again, we're just calling our function z instead of y. So this is going to be s squared times the Laplace transform of z with this particular initial condition. Okay. So using the fact that the Laplace transform is linear, I can now say I'm getting a times the Laplace transform of z double prime, which we've just figured out is s squared times the Laplace transform of z, plus b times the Laplace transform of z prime. Again, using formula 11, that's going to give me s times the Laplace transform of z minus z at 0, which is just 0, plus c times the Laplace transform of z. Okay. So, if I factor out the Laplace transform at z, I'm getting the Laplace transform at z times as squared plus bs plus c. Now notice, if I were solving the associated homogeneous equation, my characteristic equation would be as squared plus bs plus c equals 0. It would be setting this same polynomial here equal to 0. We can actually call that the characteristic polynomial for the associated homogeneous equation. Okay. So the Laplace transform of z is just 1 over as squared plus bs plus c. So the Laplace transform for z is just the reciprocal of that characteristic polynomial that we've spent so much time working with. So this is a very, very special forcing function because it means with this initial condition, the Laplace transform of my solution will just be the reciprocal of that characteristic polynomial. Okay. So now, knowing that, let's just write this down. The Laplace transform of z is 1 over as squared plus bs plus c. So now, let's work with an arbitrary element of this family. So I could say, let's take the Laplace transform of both sides. Ay double prime plus by prime plus cy equals the Laplace transform of f of t. Okay. Well, I just did the left-hand side. I know what I got there. Here I'm going to get the Laplace transform of y is equal, Laplace transform of y times as squared plus bs plus c. Again, the fact that I get just that characteristic polynomial is dependent on the fact that I have this very nice initial condition. Because otherwise, when I apply formula 11 once here and twice here, I'm getting some constants thrown in there. So this initial condition guarantees that I don't get any extra constants. And then this would just be the Laplace transform of f. But that means the Laplace transform of y is just the Laplace transform of f divided by as squared plus bs plus c. Oh my goodness. That's the Laplace transform of f times 1 over as squared plus bs plus c, which is the Laplace transform of f times the Laplace transform of z. Okay. So, I now have that the Laplace transform of y is actually a product of two Laplace transforms. So now I can say that means that y is the inverse Laplace transform of the Laplace transform of f times the Laplace transform of z, which is just going to be f star z. It's going to be this convolution. So, if I'm going to be working with a family like this, and I'm going to be solving lots of these with lots of different forcing functions, it might make sense for me to just figure out what z is. Solve that one particular differential equation where the forcing function is the Dirac delta function at 0, okay, where I've got an impulse force at time 0, and then all my other solutions will just be the convolution of my forcing function with that particular solution that I found to that particular member of this family. Okay. Now, if I'm just looking for one solution with one particular forcing function, probably this isn't the way I want to do it. Probably I want to do this when I'm experimenting with a whole bunch of different forces, and I don't want to have to do all the work of solving, then dealing with the left side again and again and again. I deal with the left side once to get z, and then I calculate the convolutions as I go through these other forcing functions that I could be trying. Okay. Now, as you're going to see it in the homework and on exams and quizzes, you're basically going to be finding one convolution, because I'm not going to ask you to do the same thing 20 times, but that's where it could be useful. When you have a situation where, for example, you've got a forced harmonic oscillator and you're just varying the forcing function but maintaining this very nice initial condition. Okay, so we'll take a look at a specific example of that in a minute. Before we do that, though, let me just say one more thing about this. Here, I've written this as f star z. Now, based on the definition of a convolution, which is that f star z is the integral from 0 to t of f of t minus u times z of u du, it's not at all obvious that that should be the same as z star f, which would be the integral from 0 to t of z of t minus u times f of u du, but they are equal. And the reason they're equal is because multiplication is commutative. So the Laplace transform of f times the Laplace transform of z is exactly the same as the Laplace transform of z times the Laplace transform of f, but this would be z star f. So they're exactly the same. Again, not at all obvious from this formula, but very nice because multiplication of functions of s is commutative, so it doesn't matter what order I do things in. That's kind of nice to know, because sometimes depending on what your functions are, it might be simpler to have one function rather than another function evaluated at t minus u, and you can choose which one you're going to do.